Okay.
There we go. Fantastic.
So I sent an email just moments ago to our little group with a couple more examples of resonance with reference also to Clifford algebra, aka geometric algebra. Did we ever talk about that?
No, but I've watched your video on on Clifford algebra and maybe more than one video. Um, Pretty
Yeah,
incredible
I've
stuff.
I've got a WordPress document, three different documents: Clifford algebra, and then the projection, and then the conformal mapping. And it's all pretty amazing stuff because using the conformal mapping, you can get all kinds of properties, such as a straight line and a circle are the same shape in this space. And indeed, spherical surface and flat plane are the same shape in this space. It's just when you have a circle that has a radius, and as that radius goes up, as soon as it reaches infinity, then the surface is now a plane. And when it comes back from the other infinity, then it becomes a sphere the other way. So the conformal mapping allows direct representation of a whole bunch of geometric primitives, from points to spheres to lines to planes to a bunch of other things. You can build a whole geometry in this conformal space that's all trapped within a bounding sphere, and that therefore the conformal geometry in Clifford algebra shows you how you can build a total geometry out of just waves, because waves can be like spherical centered. You've got a wave in the center that resonates with the sphere outside of it, and that way you can represent a point or a sphere using the same primitives, and moving to infinity. It does flat planes and a bunch of other stuff. You have to read the WordPress document.
Totally. Yeah, no, I mean I remember from your videos about Clifford algebra. Um,
If you read my visual introduction, I sent it in that email.
okay.
It explains Clifford algebra in pictures, not equations, which is, really, AKA geometric algebra. It actually demonstrates that all of algebra is actually a branch of geometry, and that all relations like numbers on the number line, greater than, less than, and so forth, that all these relations are really geometric relations. It's not an accident that when you double a distance, you get double the distance. And that geometry is locked into mathematics. That we can study mathematics not as a tool for doing calculations, but as evidence for how the brain represents reality. And that's what's interesting about math beyond
Right.
its mere usefulness.
Right. Good morning, Adam.
Hey, good
There he
morning.
is.
How you
How you
doing?
doing?
Good.
Fantastic, man.
Nice to see you both.
Are you
Um,
back in the Bay Area or?
I am, and I'm walking to the subway now because I didn't realize when I said yes, it was a 2-hour Zoom. So I'm going to be on a train for about half an hour. Uh, and then I have another meeting the last half hour, but I'll be able to be with you in either video or audio for the first hour and a half.
That's fine. No problem. Yeah. Um, well, Steve, I had some questions for you based on the email exchange we had with Richard. I hope Richard makes it. He's sometimes hard to pin down, but just to start where you just left off, do you suppose can you imagine experiments in harmonic resonance that you feel um get to the heart of this insight about Clifford algebra? Or because I noticed you're interested in the circular ripple tank, um, which I am too, but I just wonder, I mean, for me, the big ripple tank, it violates my intuition of how cognition works, because I'm assuming that there's some sort of structural necessity for, many, many small resonators to be a part of a cognitive system. Because we have all these billions of neurons, and presumably they're all resonators, but they're not like water molecules in the sense that they are just all one bed of homogeneous um, interactors. So what do you think about that? What idea? I mean, where are you with that?
Well, when you say they're not like water molecules, well, actually, they are like water molecules in the sense that the molecules are discrete entities, but water is a continuous entity. And when you splash in the water, you get these continuous responses. And likewise, with a resonating system, you imagine a sphere with millions of little resonator points. And if you could carve them out and have them run independently, they would just sit and oscillate. But as part of the larger sphere, they get coupled together, and that all of them collectively represent the shapes that they resonate as, and therefore the shapes of the resonance are an emergent property based on millions of little tiny resonators, but all of them merging together to generate standing waves that are, stable or meaningful or whatever.
Right, but I still think the difference to me is the crucial difference, which is that um, a pool of water doesn't have any memory, right? I mean, a
Oh,
pool
yeah,
of
here we
water.
go to the memory thing. Yeah, all right.
Well, yeah, but I mean, I think the memory thing is the problem that we want
Really?
to work on, right? I
I
mean,
think that's a secondary problem. First, we have to figure out the resonance and the patterns that it can make, and then invariant systems that can recognize certain patterns. So you imagine sprinkled in among all of the resonators in this sphere
okay,
um, are some that respond to, say, a spherical resonance. And when one of those fires up, it talks to the others. It's a distributed representation. And
oh,
all of them collectively get together and do a sphere. Now, by analogy with the Chladni plate, that if you had a spherical resonator and over on the side you have the Fourier decomposition, or AKA a set of resonators that are of reduced dimensionality, right? That the pattern they represent is a spatial pattern in the sphere, but the resonator itself is just a module without any inherent spatial property, except its affinity, for example, to resonate as a sphere along with other resonators. So it's an emergent principle. And when you want to get to the memory, you're kind of like saying, if you look at these resonators on the side of the sphere, here's the sphere, here's a stack of resonators. When I activate this resonator, it generates a certain pattern in the sphere in cooperation with all the other resonators that are consistent with that particular resonance. So that abstract representation that you can turn on and off to make a pattern appear or disappear in the space, that resonator would be the one that you'd want as the basis of memory, because it represents whole patterns in a simple resonance. So you could attach a memory to that and say, if you see this pattern often, then make it more likely to appear. That's a kind of memory, but it's a distributed memory that it's, I talk about it as the sphere and the resonators on the side, but really the resonators are actually embedded in the sphere. And that's the way I picture it.
That makes sense. I mean, it makes sense from that point of view, but I wonder, a memory, I still think we're talking about two different things when we say memory.
Well,
Yes.
Charlie, just one thing to say here. This is a very trivial kind of memory, right? But when you have oscillations in water and then they dissipate, there's there's frictional losses. So the temperature of the water should go up because of you having oscillated it. You know what I'm saying? Like,
Right.
so that is a minimal memory. It doesn't tell you very much, but it does tell you that something's changed.
Well, to me, like, instructing the system to remember something feels like it's against the rules. You follow me? Like, the memory should be a system's property of the history of what the system has gone through, and not something that we can encode directly by
Well,
design.
if you look at
That makes
the
sense.
example of Falstad's box modes applet. So we
Right.
have a box that has standing wave resonances in it. And on the bottom there, he's got all of these little nodes, which are each Fourier terms for the resonance that's in the box. And that, for example, if you played, say, the third harmonic in X, and there's that pattern, and then you have a Hebbian learning type of thing where if you keep playing that pattern, then that resonator grows in those little boxes. They're no longer equal. One of them is growing by like Hebbian learning that it's been responsible for painting the pattern so often in the past that now it's more ready to jump to that pattern. So you can add memory to it. And but the important thing is that you either add the memory to this array of Fourier boxes and put a memory on one of those, or you replicate that whole array of boxes, shrink it down to tiny size, and install it in every resonator throughout the system. Then the same thing would happen if you have a certain pattern appear often, then all of those resonators will become more susceptible to resonating at that frequency. So
I mean, that sounds like a plausible like avenue for experimentation, right?
yeah, but wouldn't it be important first to set up the system that it can generate all these patterns and delay or defer the question of memory to the next stage? As I said in the email, if you study a paramecium or an amoeba, they probably don't have hardly any memory at all. Well, they probably do have a little bit of a memory, like if they get stuck in a corner and feel frustration, then it makes them like explore different, like go backwards and turn aside. If they get stuck often in the same kind of hole, I'm guessing that it would be more prone to the escape maneuver just from experience. But before you even talk about that, look at how the paramecium propels itself through the water with the waving of its cilia in obviously in sort of a resonance type of architecture. and it modulates that pattern by being able to switch it into reverse to go the other way, or to intensify if it gets a strong signal that it'll, swim faster, or something.
Right.
But the learning is built on top of the resonance mechanism itself that waves the little legs, and that a model of animal intelligence should begin with, like, the paramecium that has either no or a negligible amount of actual memory, and see how it uses resonances to pattern and steer its behavior. And only when you move up the evolutionary hierarchy beyond, like, snails and slugs and mollusks and stuff, you get up to a little higher level, then maybe memory kicks in at that point. But if we're trying to start at that point, as in the history of psychology, people have started, well, how does memory work, and then they do a bunch of psychophysics and examine it that way. But if you look at it in evolutionary terms, start at the very bottom, understand the resonances in the paramecium and the hydra, and understand how different waves can promote different kinds of activity and behavior. And after we get that down, then we can attach memory to it and see what else we can get.
Yeah, let me
It's not at all incompatible.
I have a question on that, in terms of the paramecium navigating. You talk about that in terms of resonance, but it seems to me like chemotaxis or phototaxis, there's no obvious way to me that that's a resonant behavior. That seems more like a goal-directed behavior. Do you see a resonance connection there?
Well, the waving of the cilia is obviously a resonance pattern, all right? And
Sure.
that resonance pattern is observed to modulate itself in the process of exploring the environment. So what's the question again?
So you're saying that the motion involves resonance, but I'm wondering whether the motivation involves resonance. Or if
Yes.
the yeah, okay.
Yes, of course. Yes, sure. But as I say, that's a secondary problem, and not unimportant, but it's secondary to just establishing the resonance as a mode of both sensory and motor interaction. And then we'll get on to memory later on in the analysis.
I think Adam's point was that chemotaxis is sort of an aim of that behavior.
Yeah,
and
so
I think what you're saying is that it may be the aim, but the way it's accomplished, the mechanism for accomplishing the aim is always resonance.
well, for example, in the paramecium, there are probably transmembrane proteins in its cell wall that detect the strength of certain chemical signals, and that each little transmembrane protein, if it detects, a smell of food in its direction, all of them together will create a spatial pattern inside the paramecium of gradients of this bioactive medium, that if there's more food being sensed at the anterior end than the posterior end, then that larger thing, larger spatial pattern of its sensory environment inside its body obviously has a way to modulate the resonances of the cilia, for example, to make it move towards the food instead of away from the food.
I mean, the way I would think of it is that we're looking for a general purpose platform for all functions, right? Like, we're not looking for a particular function. I think the point you're making is that we should try with our apparatus to develop something that can do some functions we can obviously demonstrate that here is a function, and that could be or not be biologically relevant. But that's an important first step. I do agree with that. Adam, what is your sense of what you can contribute here? I mean, we haven't had a chance to talk
Yeah,
much.
I don't know, so I'm here to learn. What I can say is that when we're talking about new hardware, I have I have much less to add. It's been many years since I've worked in hardware. When we talk about simulations, I might have more to add, but in general, what I think I can add is perspectives from different aspects of this kind of collective intelligence, new multi-stage intelligence field. We're actually, one of the things I wanted to mention is that we're running a little conference in early December. It'll be December 8th and 9th in San Francisco. And it's actually an unconference. Have you ever been to an unconference?
No.
Can you spell that?
It's it's conference, but the first two letters are UN, like an unconference.
Unconference.
Ah,
Yeah, exactly. And the idea is that it's the agenda isn't set until all of the attendees arrive, and then the agenda is set by the attendees, not by the organizers. So what we do is we curate the attendees. We pick the people that we think are working on interesting things, and I'd count both of you in that category. And so these are people from biology, from meditation studies, etc. And essentially, we're trying to. The theme of the event is holistic intelligence, the intelligence of parts form wholes. How does that work? You can think of it as collective intelligence. Are you guys still with me? Can you hear me?
Yeah.
yes.
Yeah, cool.
We're dropping out a little bit.
Yeah,
but
sorry.
we're keeping
So
up
like
with it.
collective intelligence, you can think of it as. And we're trying to get all the different, views on this represented. So if you're free, we'd love to host you, and we can also help with airfare and accommodation if budget is an issue. It'll be around 25 people, December 8th and 9th in San Francisco. So if it's of interest, shoot me an email, and we can get you set up. That's one concrete way I can help is by introducing you to other people that might be able to help.
Absolutely. Yeah. It's
Sounds
2
good.
days. So you come in.
Yeah, you'd arrive on the 7th. There's an optional dinner that night if you arrive before dinner, and if not, no problem. But the official programming begins the morning of the 8th.
8th and 9th, and then you leave the evening of the 9th or something
That's
like
right.
that.
Yep.
Awesome. I'm just putting it in my calendar.
Yeah, send me an email to confirm if that works or if you have any questions, and we'll put you on the list.
Okay. Definitely. Yeah, especially if you can help cover our costs to get out there, that would be great.
Yes, for sure. We've got a budget for that.
Oh, thank you.
Awesome.
Thank you.
Yep.
Yeah, I mean, what Steve and I have talked about several times is just getting some basic apparatus, ordering it, getting started, and then trying to as quickly as possible get some interesting results, and then build on that.
Yeah, if you can get that done before December, then you can even give a talk on it. Otherwise, you
Right.
can give a talk on what you plan to build. And by the way, you don't have to give a talk either. As I say, the agenda is set by the attendees, so you can just decide you don't want to give a talk at all. It's fine too.
Yeah. I mean, insofar as this, whatever we end up doing, I mean, because I think Steve is a lot more interested in the analog side of things. But I feel like they all have this, this FileStad platform is already built, and it has so much code that is relevant to this stuff. I guess I'm just wondering, are you guys interested as a startup in exploring that type of coding, or are you guys still kind of going down Bayesian path, or
We're, I would say we're Bayesian inspired, but we're not Bayesian addicted. So you and I, we've emailed a little bit on this, Charlie, and I think there's more to discuss, but we have a bias that you can't solve everything with a fixed Bayesian model, but you might be able to use Bayesian mechanics to change the model such that it could solve problems it hasn't seen before. And that's a hypothesis. We're not attached to it. It's just a hypothesis. Simultaneously, we work with a bunch of different researchers, formally and informally. We collaborate with them. We sometimes even fund research ourselves that others are working on that explores other potential lenses on this, including Mike Levin for some of the experiments. So we're not doctrinaire. We just have our own priors.
totally.
Well, did you guys, I sent by email a link to the Shockley on the development of the transistor. Did you get a chance to peek at that? It's a very interesting story of how the transistor was invented. And at the very beginning, they were just taking chunks of semiconductor and putting electrodes on them and trying to figure out if it's possible to turn them into something like a transistor. And at the beginning, they were it was a fishing expedition, right? They didn't know whether they were going to succeed. That's where we are in resonance research. So it's not really the kind of thing that's eligible for a startup, because a startup is aimed at a very narrow, targeted product or something. And we're still in Shockley mode, just toying around with ideas and seeing what can work. But in counterpoise to the fishing expedition nature of it, the fish are jumping, as they say, when there's a big fish chasing a little fish and the fish jump out of the water. A fishing expedition to that spot would be a promising venture. And
Sure.
I think that with the assembly of evidence that we have from so many different sources, including Clifford algebra, conformal geometry, resonance mechanisms, Falstads, resonances, and so on and so forth, there are so many promising tidbits out there. And we also have the existence proof that biological intelligence works, and it works in a holistic manner that defies explanation in any kind of atomistic terms. The existence proof of our own minds shows that if IFFF, like in the very unlikely possibility that our consciousness is subserved by resonance, if there's a possibility of truth to that, then it ought to be investigated. Otherwise, it's a deep mystery, and modern neuroscience seems to disclaim responsibility for explaining consciousness, because that's a whole other topic. Leave that to the philosophers. But there's no other promising solution that I can see besides a harmonic resonance explanation, starting from the very bottom level with the paramecium and going all the way up to Clifford algebra and conformal geometry.
Well, also Adam's startup, if I understand you correctly, your minimum viable product is like world changing, right?
Well,
I mean, you don't have like a algorithm for morality that's sort of halfway baked.
That's right. I mean, the minimum viable product wouldn't be world changing, but it would be on the path to something world changing, I think.
Right.
Yeah. Because we want to understand this process of how agents find their role inside of a collective. Like, what is going on there? And we think resonance is one of the ways to do it. We don't necessarily think it's the only way to do it. I mentioned goal directedness. there's different aspects or different lenses you can use on this question. But the formation of collective intelligence from smaller, less intelligent parts is what we're all about. And unlike most startups, we're not narrowly focused on one particular application. It's the luxury we have as the public benefit corporation. We can serve what we think is the public interest, even if it's not a specific product yet. And it's also one of the reasons why we, find ourselves somewhere halfway between corporate America and academic America. We're kind of in this in-between zone where we try to translate ideas back and forth, but don't really know what we're doing.
Right.
Well, that's promising for us.
Yeah, absolutely. What do you suppose that if we start to configure these analog experiments, that I mean, that would be those would be consistent with your development as far as your minimum viable product? And
But
if
potentially, I mean, we've been starting with digital systems because that's our background.
right.
But we've shifted our approach before. I mean, always we've shifted to other digital approaches.
Right.
Well, the way I would think about it is if you're excited about it, which it seems like you both are, you should work on it, regardless of whether we would use it or not.
Yes.
And we could potentially fund some of the research. We could potentially connect you with people, like who knows. But
Yeah.
don't build it for us. Build it because you're excited about it.
Yes.
Yeah,
Yes.
yeah, totally. But we're just like I'm trying to, think about how to do as much as possible without getting personally financially overextended for both of
Totally.
us.
How much
Yeah.
do you think it's going to cost to run the first experiment?
I think the first is less than $1,000, but
Okay.
and then right, Steve? I mean,
Yeah, well, I think what we need to do is a series of experiments, each one demonstrating a different thing. And at some point, it will be promising enough to be fundable. But we have to demonstrate the potential with simple demos that show
Yep.
simple principles that promise in a certain direction before we're really viable for
Easy. So what I'd say is if you're looking for like $10,000 or less to just do a first set of experiments, you can just send me a quick email that 3 paragraphs or less. It doesn't need to be a big presentation. Like really simply, what's the hypothesis? What's the method you're going to test? What are the results? And how long you think it will take to get results? That's it. You could write that in 5 minutes. And if it's $10,000 or less, I can just approve it within a week. If you're looking for like $1 million, then we need something. But seed grants, seed funding, we do that all the time.
okay.
Yeah, well, I would
Fantastic.
propose let's get a first couple of demos going and on videotape, and then we'll send the email. How does that sound?
Even better. That's even better.
Yeah.
And then the best thing to do is to come and join our, if either of you or both of you can come and join our event, there'll be a bunch of people who are also funders there, who do much larger investments. If you're looking for funding or, other collaborators, we're trying to create this ecosystem. That's kind of how we see ourselves. So we do a little bit of funding ourselves because, we want to get the ecosystem thriving. But we're not venture capitalists, we're not foundations, we're not big money, we're small money, and then we help to organize the bigger money.
Definitely. Okay. Fantastic. Yeah, that's totally awesome.
Yeah, you bet.
I mean, that's the way it's got to be done. It's got to be done with a lot of collaboration because,
That's right.
This is not just it's not just a small picture problem.
Yep. Exactly.
Okay, well, fantastic. That's really helpful. Yeah, and meantime, as we go through these analog configurations, I'm assuming that there's always a digital sort of version that could be that can be imagined, right? And if we have this like Falstad, I mean, I'm assuming we're not going to uncover anything that hasn't already been sort of is like not congruent with the math that underpins, you know,
Well, we could also potentially um, uh, get Falstad to write specific code for us. And, I'm sure we could commission him for some reasonable fee, but there's things I'd like to do to Falstad's simulations to make them closer to what we're interested in, like a spherical resonance with a variable refractive index. If you read my recent email, which I only just posted moments before this meeting, but yeah, that would be a possibility. Get the real expert who knows how to write the code. I've tried to do stuff like that, but it's kind of beyond me now. I'm getting older. And my coding skills are not quite what they used to be. But
that's a great idea, Steve, to get him to possibly get him his help with it, because he's done the most,
yeah,
that we can find out there. So
yeah,
Where is he based?
I don't know. I did email him about 10 years ago, telling him how much I loved his site, and we had a little exchange. But I never told him about my harmonic resonance theory and how his code might be modified to reflect that. So I'll try to get in touch with him and see what happens.
awesome. That's great. Yeah, so okay. Well either way, I feel like it's easier to go from analog to digital than the reverse, maybe, or I'm not sure.
Do them
But
both. Do them
yeah.
both. Yeah. The analog
Yeah.
experiments are appealing at an intuitive level. If you can demonstrate complex behavior using just resonances, that would be more impressive than a Falstad simulation of the same thing. Although that the latter would actually be more analytically confirmed. It's actual equations and stuff. So I say do them all. Do them both. Do them all.
So if I'm understanding you correctly, Steve, you're one of the configurations you're most fond of or interested in starting with is the idea of this circular ripple tank with the piezoelectric resonators and tweaking them in a similar manner to the Japanese artist that made the corporate logos appear in the water.
Yeah. No, you never actually saw that picture, did you?
No, I don't
Yeah.
know.
Well, I searched and searched. I can't find it again. And I tried to track him down to his organization, and I failed. I couldn't get a hold of him. So it's just an existence proof that you can do it. But if you think of it theoretically, it makes perfect sense that if you had the right vibrations coming around the pond, you can generate any image in the pond. It's like it's like Fourier theory itself, that any image can be broken down to its Fourier components.
Right. Yeah, I mean, the proof of concept is there in that that experiment was done and it worked, presumably. But do you feel that you understand the math that would be needed to make that
Did
ripple
you
tank?
see my email discussion on that, where you take an image and you produce a Fourier transform, and then at every radial angle, you read the transform to see what frequencies it contains, and you feed that to, say, this pair of resonators opposite to each other, And as you go around the Fourier transform, you can feed the other resonators. And then it's just a matter of getting like what it is, a
Is it
parallel waveform stream for
okay
each of the pairs at each of the orientations.
at each of the, so is it, but is it the same as the phase conjugate mirror or no?
No, this is
Okay.
linear resonance.
Okay. All right.
But phase conjugation is so powerful. All you got to do is crank up the amplitude, and then you get the phase conjugate effects. I sent in my email, I sent a picture of waves in the Blindman Canal in Gloucester here, crashing into each other and demonstrating nonlinear wave phenomena. And I went down to the beach and
Oh,
found,
these are, oh, I see. These all came in. These emails just came in like today. Okay.
yeah,
Or
yeah, sorry about that.
I can't, this is from yesterday. I see.
Yes, yeah,
Oh, beautiful. Okay. Yeah, sorry, I was doing other stuff this morning and didn't
yeah, no,
get
that's
into your emails. Now I wish I had jumped on that right away.
well, that's okay then.
Oh goodness.
We'll have
Okay.
to, yeah.
Okay, so you have a handle on how those pairs, how that can be computed.
Yeah. Well,
Okay.
if you think of just a linear ripple tank that can only do waves in basically, 2 dimensions along a slice, and you put resonators at the end of those. And if you took the Fourier transform of, for example, a square wave pulse, then you look at the transform, and then in 1 dimension, the transform will tell you what frequencies you need, and you could oscillate those resonators to regenerate that waveform in 1D or 2D, depending how you consider it. And if you do it that way, then you can do it at every other orientation as well. So that might even be a way we might walk into that experiment. Start with just a 1-dimensional flat,
Uh-huh.
a wave thing.
Right. Okay. So make a ripple tank that's long and skinny
Yeah,
begin with resonators each end, and then
right.
generate a pattern based on the Fourier transform, and then do more.
Yeah, and there's going to be a lot of trial and error. For example, the resonators, they're not like woofers. They can't do big low frequency oscillations. So they'll do tiny, buzzy little things with ripples, tiny ripples. But maybe we need to get the equivalent of, woofer resonators, and actually just dismantling an old woofer speaker. You could, cut away the whole cardboard cone and just use the part that actually does the motion and use that as a resonator. Maybe we can get lower frequency, energetic kind of stuff.
Isn't there a lot of stochasticity that's introduced by the metal of the tank and the like platform it's sitting on and that sort of thing, or is that not as important?
Well, if you had waves sloshing around in it, that's not going to be affected by, say, vibrations of the lab desk. It's a coarser phenomenon. Now, if we were going to do light experiments using laser light, that would really be great. But then you need a real official light table with all this fancy gear, and preferably someone who's familiar with all that stuff. So
That sounds more difficult.
yeah, well, when I used to work at Avco near Boston, they had a light table, but the whole building, just by the nature of it, was kind of a swampy-ish area. So they raised the whole building on cement poles. And the whole there was a parking lot under the building where the people would park, but the whole building was able to resonate because it's standing on legs. So they had a light table but those light tables, they had to bore 4 holes in the floor and send their own 4 columns, cement columns, straight into the ground. And the light table was mounted on that to eliminate the vibrations of the building. So it's really sensitive, touchy stuff. But if we could collaborate with a lab that does that kind of stuff, that would be very helpful.
Well, just taking that same idea in the other direction, do you suppose that ultimately, if we work it out on a long, thin ripple tank, and then we work it out in a circular ripple tank, do you suppose there's a way to configure a sphere, a globe, a ripple globe, that with some, other material inside the water that can be moved around by resonance, so that we could have a
Yeah,
giant ball of water with resonators all around it, right? And then some sort of material that's a different color, suppose, in the middle of the water that gets jiggled into the configuration of like a human being, whatever you want, like some morphology that we get from nature, and we sort of, that seems like, in terms of
problem with 3-dimensional resonances is trying to make them visible. And there are different techniques used. There's this fellow Murray, Murray. He had an article in Scientific American a decade or more ago, and he was showing how tiger stripes, zebra stripes, leopard spots, all the different types of camouflage patterns that animals have on their hides. He had a feedback chemical model, but then to sort of verify the model, he cut out these little pieces of tin that were shaped like an animal hide. It had, a body and 4 legs and a head and a tail.
Right.
And vibrated them with different signals that reproduced the tiger stripes and leopard spots in resonance on this piece of vibrating steel. But resonances are very tiny. It's like, within a wavelength of light, perhaps, depending on how hard you bow it or whatever. But he had a system for viewing these by illuminating the vibrating plate with a collimated laser beam. So not a little skinny one, but it's diverged out into a parallel beam that covers the whole plate. And they make the plate shiny, so when the light hits the plate, it gets mirrored straight back up its path. Now, if you move that little piece of tin up by a wavelength of light, it'll go into like cancellation mode.
It won't hit.
If you move it down, then it's in the positive mode, the reinforcing mode. So you can make these tiny oscillations or movements visible, but since they're oscillations, they'll be going bright, dark, bright, dark, bright, dark, 30 times a second or whatever. So you flash the illuminating light, you send it through a what do you call that? Like a spinning disc with a segment cut out. And when you view through it, you can only see light whenever the window comes by. And you spin the disc at the same rate that that the oscillation goes. And if you take a video and you turn a knob that adjusts the shutter, to turn the speed of the shutter until it matches the resonance, then you'll see a steady pattern where when it bends up, flash, then it bends down, then nothing, and then it bends up, flash, and it always catches it on the upstroke, and then you can record the pattern.
Right.
So
I remember you explaining that, but what I don't understand about that example is, why wouldn't you just make Chladni plates? Like, why didn't you just put sand on the metal figurines instead of?
Oh yeah, sand is messy. It goes all over the place. It'll get into your carpet, and you'll never be able to vacuum it out. And so sand is kind of a messy way of making the visible. He could have done that.
Could have.
as
Okay.
well, but he had
So
a
what you're
better-
saying is that the if we made three-dimensional waveform patterns inside a globe of water or whatever, the difficulty would be seeing the difference in pattern between the outside of the figure and the inside, so to
Well,
speak.
can you bring up that email that I just sent that you haven't had a chance to read?
Okay, let me share my
Let me scroll on down to the relevant part.
share. Can you see that?
Yep,
Which one is it?
more resonant stuff. The top one there. Whoop, where'd it go?
More resonant stuff. Okay. All right. Okay, here's another book I started
Yeah,
writing.
okay, wait. So this is
Okay.
another book I started, never finished. It's about harmonic resonance in the brain, talking about resonances as a very general principle. Those are atomic orbitals right there, showing that resonance goes all the way down to the very bottom and then some. Now look at this thing here. Zoom in just below it there, right there. That right there. Zoom into that. Can you zoom in? Yeah. So what we have on the left is an acoustical box, like the box modes applet in Falstad. And at each
Right.
location in the box, there's a mechanism like B at the top right there, which is a microphone that picks up the vibration of the air in the box locally, and two diodes counter biased against each other. So when the sound wave goes up, it's green, and when the sound wave goes down, then it's red. All right, so these two, the red and green pair, will be flickering at the speed of vibration of the sound that's trapped in there. But then, as I was talking about the shutter with a gap in it that spins round and round, well, down here in the bottom right in C, there's a sync pulse. You see, it's a square wave, and you choose that square wave to be on only in one phase. So in this case, it's on in the green phase and always off when it's in the red phase. And so that sync pulse can filter out and demonstrate or reveal standing wave patterns like, and then scroll down a little, there's Falstad's box modes applet. So scroll down, there you go. And so some of these kind of phenomena could be demonstrated as they are demonstrable in Falstad's simulations. And while we're on the subject, let's scroll on down. In this book, which has never published,
What you're saying is you could configure a Falstad box
yes,
such a way as to
make the waves visible.
generate any shape you want. You could generate any shape you want with it,
Yeah.
in principle.
Right. And then I was worried about the infinity problem. If you scroll down the colored picture there, B is a sinusoid that goes on to infinity. A uses gradient refractive optics to squeeze the waves at the ends, potentially all the way to infinity. And now what you have is a wave resonator that's capable of resonating essentially an infinite pattern at finite resolution. And then if you scroll down a little more, look at those spherical pictures, scroll down some more.
Yeah.
That's the kinds of patterns you could generate in a resonance that has that kind of property. Now, scroll down just a bit more. Ever since I learned about conformal mapping and Clifford algebra, I've revised my theory, and then I now propose it's all done with projection. And here's some, look at those two blue spheres there. That's a conformal mapping inside the sphere of the world that's outside the sphere. So for example, there is a red line, and in the sphere you see kind of a conformal reflection of that red line. And that reflection is shaped like a circle because, and you see that in fuchsia, that circles and straight lines are the same shape in this space. And if you scroll down, you can move that all into 3 dimensions. You have to read through it, but talk about what the potential for resonance is, that in resonance, you can make spherical resonances and you can make linear resonances. And using projection, you can make conformal resonances. And by that means, you can represent a whole geometry of different shapes based on the primitive of point, sphere, and line, and they all come right out of the math in this WordPress document that these are extracted from. I explain it in more detail.
I see the
So,
connection. I mean, I do see the connection. And I'm trying to put together the I guess one of the things I'm trying to figure out is how to transition between the abstract and the concrete here, because we want to have
yeah,
concrete demonstrations
yeah.
uh, that
Well,
somehow give insight into um,
yeah.
abstract representations. So that's a
Well, I recommend you read that whole Clifford algebra thing. There's 3 parts to it. The first part is just Clifford algebra. And my interest in it is that Clifford algebra is like a window into how the mind works. And there's 3 parts to the presentation, just Clifford algebra itself, and then Clifford algebra with the projective geometry, and then finally Clifford algebra with the conformal geometry. And all of those really highlight the potential of resonance for representing shapes. So take a gander through that, see if you can follow it. It's explained in pictures. So it's designed to be intuitively understandable. And
I mean,
I think,
what one of the things that interests me about all this is that if you can somehow build this bridge to representing things in shapes and geometry, it does seem like that's at least the first step towards representing causation.
yeah,
You follow me? Like
that's
some shapes are compatible with one another and others are not, and motions, impact, and it sort of makes the um otherwise vast and intractably confusing landscape of ideas. It makes it somehow more orderly, makes it more evident how certain structures conflict with one another and other structures don't, right?
yeah,
uh, which to me is like the first step towards understanding causality, and that's kind of how what I think of as the holy grail. The difference between prediction and understanding is that understanding has got some sort of causality built into it.
yeah,
you've got a model in there that says, okay, there's entities and they're shaped like this, and there's forces and they do things like this to the entities, and there are certain things that can happen and other things that can't happen based on what each entity and force can do. um,
let
which
me
to me that's the mystery of understanding versus just predicting based on data, based on correlation, what's going to occur.
trying to find a part of my book here. Um, Well, I can't seem
I,
to find
are
it.
there analog ways to build these resonance? Here it says a resonator whose grin profile reaches infinity at the ends will
Yeah,
sustain.
well, I'm not even
Are there
sure if
analog
that,
ways to build those?
well, as I say, that was a proposal I made, which I have since retired because I think it's done with projection, not with gradient optics. I'm not even sure if the gradient optics is possible. Can you make a rod of glass that has like infinite refraction at the ends and blends to regular refraction in the middle? Now I think it's all done by projection, as in Clifford algebra and the conformal projection. So I think you might want to read that whole Clifford algebra thing, all three parts, and see if you can follow along with it. And I think that that might be helpful.
Okay. I
So
mean,
are, are we about done for today?
well, yeah, just about. As far I don't have that much more to add other than let's get started.
Yeah, right, right.
You placed some orders. You ordered some stuff already then, or
Yes, I've got the lab bench has come in,
okay,
and I haven't bought any of the piezoelectric devices yet. I see that there's a large variety of them with different properties and very different prices. So the first instinct, get all the cheap ones, get a handful of them, and
yeah.
then look into the other ones, see if they have a better low frequency response or whatever.
And what about a ripple tank? What do we think we can use? Trash can
Well,
lid.
yeah, almost anything really. I think nearby there's a store called the Container Store, and it has all kinds of containers of all different shapes and sizes. I'll browse through there and find a circular one or and a linear one and whatever else.
Okay. Yeah, we'll just, let me know when I can come down and spend a day or two with you.
Yeah, sure, sure. Let me unpack a bunch of gear and place some orders, and then we'll take it from there.
Perfect.
Awesome. I'm very excited to hear about this. Charlie, where are you based again?
I'm in Vermont. I live in
In
Guilford,
Vermont.
Vermont,
Okay. Nice.
southeastern Vermont. So I'm probably
Yeah,
2 hours,
yes.
something like that.
Awesome. Well,
Yeah.
hopefully you can both come out. Shoot me an email if you can. And maybe you can be on the same flight. We'll have a couple other folks coming from the Boston area, I think.
Great. Okay. Absolutely. That'd be
Yeah,
fun. Are you gonna get Mike Levin out there?
No, Mike does not travel. But we're gonna invite one or two folks from his lab.
That'd be great. Yeah,
Yeah.
it'd be fun to travel at the same time as them. So
Yeah. Yeah, I'll keep you posted on that. But definitely first step, just let me know if you can make it, and then we'll mark you down and get the wheels spinning.
um,
okay, yeah, I'll send you an email. I don't see any conflicts just glancing at my calendar, but
Great.
be
Great,
sure.
great.
Right on. All right.
Mike
Well,
Mike Levin is a very common name. How can I search him up?
Oh,
Where does he work?
Charlie can send you all of his stuff.
All
oh
right.
man, he's all over YouTube. Yeah.
Yeah.
He's all over YouTube. You'll find a lot if you Google Mike Levin on or look him up on YouTube. He's got uh, probably hundreds of videos.
On what
Um,
topic? What should I search under?
it's mostly regenerative biology. I guess would be his topic.
All right. Good.
Oh yeah, there's some great lectures. Really
Um,
interesting stuff. Planaria is his favorite organism.
all
Yeah.
right. So are
Awesome.
we all done for today?
I think so, yeah. Unless you
Yeah,
guys have
awesome.
no, yeah,
No,
it's
that's it for
recorded
me.
too, so yeah, we
Great.
can we didn't get to talk about Richard's initiative, but that's because Richard's not here. So
Yeah.
All right.
All right.
all right,
Yeah,
guys.
All right.
Okay,
We'll
sounds
see
thank
you
you
good.
guys
so
later.
much. Yeah,
All right,
see you
cheers.
later. Okay, bye-bye.